I guess we get started. Here's our attendance form for our one attendee. Hopefully somebody else shows up, but if not, that's okay too. Just some announcements before we get into the lecture. I have released Hack Challenge Measure Pairings. Apologies for it taking so long. That's partially my fault for poor communication with the Hack Challenge coordinators, but they are out now, and so if you have any questions for, like during the Hack Challenge with anything that you're implementing, or logistics about the event, that's the person you'll want to go to. I should have emailed everybody separately about that. But yeah, let me know if you have any questions about that. And one thing is that you are technically expected to organize a midpoint check-in with your mentee or your mentor for the midpoint submission deadline. It's not required though, and I understand that over Thanksgiving break you may not want to, and given the limited amount of time I've given you, because I assigned the mentor so late, you might not want to. So that's totally understandable. But if you'd like to have some clarification on the project, there is projecting. But yeah, if you'd like any clarification before your midpoint check-in to see if your submission looks good, that's what the midpoint check-in is for. And we have one last bonus lecture next week after this one, where we will be wrapping up our I guess, diving into Jetpack Compose by me showing you some sneak peeks into the new user. Now, I'm not sure I'm supposed to be showing you that, but I'm not going to ask for permission. I'm just going to do it anyways. Okay, attendance form for you as well.
Oh.
Some bonus points. Okay, awesome. So today we will be going through a little bit of a break from Jetpack Compose, from that framework, and diving into a little bit more of a deeper understanding of Kotlin and some of the cool stuff that Kotlin provides that Java simply doesn't, and makes Kotlin, in my opinion, the superior language for Android development. So, Kotlin is built off of Java, and therefore it is like Java in many ways. A lot of the syntax is pretty much shared, and it is, basically if you're coding in Kotlin, you'll see a lot of remnants from Java, such as .class and other sort of things that clearly show that Kotlin is built off of Java. However, Kotlin is in many ways better than Java, or in just some ways different from Java, that make it more suited for Android development. And one of the biggest strengths of Kotlin, and probably the most notable one that I'm going to be talking about today, is its inclusion of functional programming. That is the title of a class here called CS3110 that are either you taking, you're taking. Okay, awesome. So some of these concepts will sound very familiar to you, and I'm sure you'll be taking in a future semester. So this is a sort of introduction into some of the basic ideas of functional programming that you see in Kotlin. So first, with functional programming, or before I guess diving into functional programming, we've all seen that you can define functions in Kotlin just like this, just pretty much how you do it in Java, just with a little bit of syntax mixed up here and there. Where you just declare a function with the fun keyword, kind of like how in Java you do something like public int fact. Here you do just fun fact. Fun fact, interesting. Anyways, so this is one way that we've seen that we can declare a function in Kotlin, but we have also seen another way, right? There have been other ways that we can declare functions, and the main other way we can do it is, well, I guess I can remind you, is with click listeners. And so how do we do it with click listeners? Well, we can declare functions to pass into click listeners that don't really have a name. And these functions are usually called anonymous functions, hence anonymous being the fact that they have no name, or lambda functions. And these do exist in Java. Pretty much the anonymous function is the, I don't know if you can see my cursor, just this curly brace stuff here. It's basically the code that you put in here, and it's essentially a function that you're passing into the onClick listener that executes every single time you click the button, every time you click a listener fires. And so these functions are another way we've seen that we can declare functions. So we can declare Java, but have you seen this in Java? So we have a variable here now. We have a variable called print names, or print times. Let's see, maybe give it a mouse here. We have a variable named print times, and it's holding onto a function. As you can see here, this is a function that's taking in a string and an int and returning nothing. And it's pretty much printing s, which is the string count amount of times. And this is being stored in a variable. Now, that is not something you can do in Java. You can't hold functions as variables in Java. And so how is this working? How can we do this in Kotlin? Well, one of the main pillars of functional programming is that functions are values. And so anywhere that values can be used, that's pretty much like literally anywhere that you can use values, functions can also be used too. And so this is why in the previous slide, we can store a function as a value to a variable. And this is obviously not possible in Java. You can and will most likely dive into a lot more about functional programming with CS3110 and OCaml, the most infamous language on campus probably. But we'll be just going over a sort of a very brief, sort of surface level overview of functional programming that Kotlin implements from these other functional languages. So functions can be used anywhere, as I said on the previous slide, including it as parameters to functions. So you probably saw this on your homework 6 with the callback function that you pass into, or was it homework 6? Homework 5, where you pass into the get picture callback from the URL. You would basically pass a function that would take in the URL and do something with it, and you'd pass that as a parameter to the get picture function. This is pretty much how that is possible. It's because functions can be used as values, and hence they can be passed as parameters to functions. So here I have an example of one way you can do that. I have a function here that, as you can see, as one of its parameters, takes in a function. This is a notation to say that the function must take in no parameters and can return anything, including nothing, and the function itself would return nothing. So you take in the function here, and then you execute it twice. So that this function is aptly named do thing twice. Oops. And so all these functions that take in other functions are called, I didn't press anything here, are called, wait, what? Am I going insane? Okay. These functions that take in other functions are called higher order functions. And so we'll dive into a couple more of these higher order functions, some of which are more useful than just the twice function. So there's a lot of usefulness to be had, and a lot of code condensing by allowing functions to take in other functions as parameters. And so on collections, that's like stuff like lists, sets, mutable lists, and whatnot. Some of the most important higher order functions you'll see are map, filter, and fold. These are all over our code base on eRead and on other apps on AppDev as well. They're everywhere, they're super useful, and condense your code so much, as we'll see in the demo later. So first, map. What is map? Well, the idea of a map is that, say I have a list, I can create a map list, or a sort of mapped version of that list, by taking every element in my original list and doing something to it, and then putting it in my other list. So for example, I could make a mapping of the list 1, 2, 3, 4, 5 or I could map 1, 2, 3, 4, 5 to 2, 3, 4, 5, 6 by taking each element and adding 1 to it. So I take the element 1, add 1, put it in my new list, and keep doing that until I have my new list after I've iterated kind of on every single element. Same thing with the hello goodbye. I could say for every single element in my list, append world onto the end of each string to get hello world and goodbye world. A little sentence. I can see why programmers default to hello world instead of goodbye world. That one's a little bit, that's a little grim. But anyways, those are some examples of mappings, and we'll get into how we can actually use a higher order function to do something like this. Because this idea isn't necessarily difficult. I'm sure you could just do this with a for loop or something like that. But mapping makes it so much easier and so much more condensed, as we will see. But anyways, moving on to filter. As you can probably guess from the name, filter can take out certain items from the list, or I guess more accurately, create a new list which has only certain elements of the original list. So I can take my original list, 1, 2, 3, 4, 5, and I can say, okay, every element greater than 2, I don't want. only want elements less than or equal to 2. Either way, I'll get the result filtered as 1, 2. And I can say the same thing for hello goodbye by removing every element with like 5. So the new result would be goodbye because I've sort of filtered out hello in that case. So pretty basic. And finally, fold, which is probably the most interesting and probably the most difficult of the 3 to understand. So sometimes you want to iterate over each element in a collection or in a list and accumulate a sort of result along the way. So that result could be, for example, a sum of every element of the list, or it can be pretty much anything. So anytime that you want to accumulate a result in which every single element contributes, you'll want to use a fold. So I could say, take 1, 2, 3, 4, 5, and fold by summing up all the elements to get 15. And I could also fold my list of strings by, say, concatenating every single one until the end, until I get a massive string in the end result. So fold is basically accumulating a result. That's the big idea. And so how are these functions necessarily higher order? Because I've shown you all these things that higher order functions can supposedly do, but as you probably could have reasoned out of your head, a lot of the things I just told you don't really need a higher order function to do. You could just, for example, take a for loop to sum over the elements in a list, no problem, right? So why are higher order functions actually useful? Well, we will see with a little bit of a demo. So this demo is going to be a little bit different from what we usually do, since this is just purely Kotlin. I have a VS Code window open here instead of the usual Android Studio, and I sort of made a little bit of a playground here to examine these higher order functions. So right now, I basically just have my list of 1, 2, 3, 4, 5, and let's go through some use cases of mappings. So say we want to duplicate my list, or make a sort of duplicated my list with all the elements with just +1 added to it. We could make a function like this, as you probably could have guessed, where we just make a new list and add every single element of I, or the list at index I by iterating with a for loop, except adding 1 to the element. And this, as you probably could have guessed, will just do what we originally wanted. You take every element, add 1, and make a new list. So if I see what this prints out, run the code really quickly. This sometimes takes a little while, maybe like 7 seconds or so. This is why Gradle lists take so long. Kotlin is kind of slow. But anyways, so I didn't save. We'll do that one now. You can see that the printed out list from the functions, not surprisingly, will be 2, 3, 4, 5, 6. You just take every element and add 1 to it, right? But now let's say I want to do something else. I have another goal in mind. I want to instead take every element of my list and multiply each element by 2 to create a new list. So essentially doing the same thing, but instead of adding 1 to each element, I want to multiply by 2. In order to do this, I have to create an entirely new function, essentially, where it almost looks the exact same, except this little part is different, where instead of adding 1, I'm multiplying by 2. But I'm nonetheless still iterating over the thing, creating a new list, and returning that list. Everything else is the same, besides just this tiny little segment where I'm actually telling the function what to do with each element. So this sort of code reuse is very bad for higher and bigger systems. You want to, at all times, minimize the amount of code that you're just copy-pasting in your program. Because I know that when I made this function, all I did was take this, copy-paste it, change a few names, and change this to ×2. That's all I changed. And, well, anytime you're doing that in code, you should see that as a red flag. There must be a better way to do things. So, obviously, if I were to print it out, it will, unsurprisingly, just print everything with ×2. So 2, 4, 6, 8, 10. And as you can see, these are the 2 results. Now, this code reuse can be eliminated with the use of map. So what exactly is our mapping here? Well, in the first case, we're mapping each element to the new number where we have that element +1. And this is the sort of way to think about higher order functions, is you're not really thinking about the whole collection, but one element, but rather one element at a time. So I'm thinking, for my mapping, I want to take each element and add one to it. So that's exactly what I'm going to make my map function do. So we're going to say, make a new list where I'm going to say my plus one list equals my list dot map, and this is a function built into Kotlin. I'm going to say, well, map takes in a function that takes in an element and does something with it. So E here, I can treat as an element of my list, an arbitrary element of my list. It could be 1, it could be 2, it could be 3, it could be 4, it could be 5, or I guess at some point it will be any of them. So I need to treat it as if it's any element of the list. And then the result of this function, the sort of return of the function, should be what I want that element to become. So in this case, I'm going to take my element and add 1 to it. And let's print that out. And notice that is just one line of code. And see the print result. And suspense is the exact same thing. So in one line of code, I've done the exact same thing as what, 5, and I can do the exact same thing for product, not by copy pasting that entire thing, but say, I guess I'm still kind of copy pasting it, but I'm only copy pasting one line, so it's not really as bad. So I can take every element, and instead of, so I'll call this like my product list, something like that. And I'm going to take each arbitrary element and instead multiply it by 2. So let me print that out as well. Product list. We'll run that. And again, in one line of code that I typed in like maybe 10 seconds, it does the exact same thing as this whole function with that whole for loop and creating a new list and whatnot. So as you can see, higher order functions do have a good amount of utility in reducing the amount of code that you have to write. And that's just a map. So the idea of map is that you want to create an entire new list of elements in which each element maps to a new thing. So in this case, it would be 1 mapping to 2, 2 mapping to 3, 3 to 4, 4 to 5, 5 to 6. It makes a new list that's the exact same size as the original list because it takes every element and maps each element to something else. Okay, now moving on to filter. So let's say for my use case that I want to filter out all the odd elements out of my list. I can do a very similar function as before where I basically iterate through the entire thing, make a new list, and add only even elements to that list. That's modulo 2 equals 0. So again, very similar function to what I had before, except it's a lot of lines, right? And as I'm sure you could have guessed, it will end up printing 1, 3, or 2 and 4. I won't show that now. I'm sure you can trust my coding ability. But let's say that I want to filter out all elements that are greater than 4. I have to again do the exact same thing and copy paste that whole function. So how can I do this instead with a filter? So how a filter works, what was my first one? Even list. Is I will take my list and do dot filter. So I'm trying to read the spec of this thing, it's kind of terrible. Basically what you can see here is predicate T to Boolean, that's the important part. That's what the filter takes in. And basically it'll take in a function that takes in an element and returns a Boolean that tells the filter function whether or not to keep that element in the list. So again, we're operating on arbitrary elements, which I'll call E. And we want to keep E, that is a number in the list, if it is even. So that's E mod 2 equals 0. And so every single arbitrary element will be accepted into the filter if this is true, which is basically saying each element will be accepted if it's even. And again, instead of having to iterate over the entire list, I'm only reasoning about one element at a time, essentially, when writing my function here. And I can do the same thing for the, greater than 4, less than 4, less than 4, where I'll write my filter function and accept every single arbitrary element if it is less than 4. And that's it. These 2 lines took hardly any time to write, and they do the exact same thing as all of those. And to show that, I will print these out. My less than 4 list. And run that. So I have those other print statements up here, so they should match the filter statements. And they do end up matching. 2, 4, 2, 4, and 1, 2, 3, 1, 2, 3. So again, a lot of code cut down with the use of higher order functions. And it's honestly kind of elegant. It's just a one-line solution as opposed to this blob that nobody wants to look at. Okay, so the last higher order function that's of pretty high importance. I'll just comment on all these groups. We comment all the print elements. So the last higher order function we'll be talking about is fold. Now there are a good amount more that Kotlin offers, but these are definitely the 3 most important, the ones that I see most often on our code bases on AppDev that are very reminiscent of functional programming. There are some other ones that are sort of mixed between imperative and functional programming, so we won't go too much into those even if they're useful. But fold is the last most important one. So again, the idea with fold is that we want to sort of accumulate results by iterating over our elements in our list. So say that we want to sum up all the elements in our list. We can do that with a function that iterates as very similar to that before, where you just take every element, sort of accumulate the result in this sum, where you're adding the new element every single time, and then you return it. Nothing too crazy at all. Uncomment that print. And now let's say we want to accumulate a new result that's basically the product of all the elements on the list. So I can, again, almost do the exact same thing, except changing maybe a few numbers here and there and changing this to a times. So again, code reads, and it's terrible, even though we're almost doing the exact same thing. So something like this is where we'll want to use a higher order function to just say, okay, do this iteration for me, but change one little thing. I want you to multiply instead of add. That's something that a higher order function can do. So, again, let's use fold here. So my first one was a sum, so let's say my sum. Now, unlike the other 2, this does not have to return a list. This can return pretty much anything. Your fold can be a lot of things. It can be, well, anything. And I guess the most sensible thing is that you return what the list contains. So in this case, I have a list of ints, so I'll most likely be accumulating the result of an int. That's the sum of all the elements on the list, which is not a list. It's just an element, or it's just a value, essentially, which is separate from fold and map, which return to lists. But in this case, just to push the point home, my sum is an int, and I can fold over my list. Now fold here, if I roll over it, you can see it takes in now 2 different parameters. It takes in an initial r, which is basically the initial value for the folding, and then it takes in your function. Now this function takes in 2 arguments, but we'll get to that in a second. So our initial value for our sum is probably going to be 0, right? Makes sense. And then we need to pass in our function. So our function, now let's think about how many parameters we need here. So our function, let's say we just wanted to operate off of a single element here like we were doing before. Well, how do we exactly tell the function now, I want to accumulate anything? It's obviously not enough. I can't just write like e, because I want to do e plus and then whatever is currently there, right? Whatever my current accumulation is. So fold takes in another parameter, and it's usually written as ACC, which stands for accumulation or accumulator. And it basically holds the value of what you've folded so far, what you've collected so far. So it's whatever, for my arbitrary element E, whatever I've collected up till this point. So I can then return my previous accumulation plus ACC. And so this basically takes whatever my previous summation was up until this point, and then tacks on an E sum on the end of that, pretty much. And I can do the same thing for the product. Where I do fold, this time it'll be initial value of 1, because if I had 0, the product would just be 0. Take in my accumulation and my arbitrary element, and I'm going to take my previous result and multiply it by E. And of course, let's print those out, see if it's the same thing. My product. And run that. And let's see if they do come up with the same results. Oh, I'm gonna an error. What's up with that? Wait, that should have been an error. Let me just comment these guys out. It's yelling at me because I'm not using them. Okay, let's try that again. Okay. And as you can see, it is printing out the same stuff. And once again, with only one line of code. Now, I think you get the point. Higher order functions, super useful, and condense your code down by a lot. So let's move on from this whole just 1, 2, 3, 4, 5 thing, and go on to a little bit more of an involved example. Comment that out. Thank you for showing me that, by the way. The multi-line comment, that's super useful. Okay, and then the multi-line uncomment. Cool. Okay, so let's say I have a list of string costs. So these strings are, say I'm like an employee or whatever, like a boss, watching over a bunch of employees, and I tell them, okay, I want you to type into your computer what costs that you incurred for the day. And so, say we have a couple of nice employees here who actually type in the correct formatted thing. You have a guy whose cat stepped on his keyboard, another memer, and somebody who, I guess, hit enter too early. So these are a couple things that, well, some of these elements will have actual value. That's all of the things here that I want to eventually add up to my total cost. And then I have things that don't really mean anything that I want to take out. So this problem of, I guess I'll just go to the problem, of summing up all the utility costs properly formatted into a float. So whatever these string values all sort of parse as a float, I want to take all of those float values, only the ones that are valid, and then add all of them up into my total utility cost. That's basically what I want to do. So I want to take 583 plus this, 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 and sort of ignore these other ones that clearly aren't costs. So we can employ all of our higher order functions, all of filter, map, and fold in order to do this pretty concisely. So I guess our main procedure is that we will first filter out all of the bad strings. Let's filter out all the strings that aren't formatted correctly. So we want to make a filtering where we take out this string, this, and this that are clearly not like the $sign and then a float amount. We want to take all of those out with a filter, which will return a new list with only the correctly formatted strings. And then we can do a mapping where we take every single string that's valid and then map that to the float value. So say 30.00 would be mapped to the actual float, 30.00. We do that mapping, and then we fold the sum to our final cost. And just to sort of help with this, I've created a little bit of a helper function that takes in a string and tells you if it's parsable into a float or not. So if I were to pass in like 1.0, it would return true. If I were to pass it in like high, it would return false. Just a small little helper function to make it a little bit more concise. So first, I guess I can make my list. So I'll call it, I want a final result, right? So my total cost. And I want that to be a float. So I can take my list dot my predicate? What do I actually want to filter my elements based off of? So I just operate off of a arbitrary element and say, actually, let me just get rid of my type here, or else I'm going to have right squiggly lines all day. So let me operate off of my arbitrary element E. So when do I want to accept an arbitrary element E? Well, I want to accept it if it's off of this note, right? So each string has to be first non-empty, have a first character of $, and the substring otherwise after that has to be parsable into a float. So I can take those sort of guidelines and make a Boolean expression out of that. So I can say, okay, it has to be non-empty. I can say E dot length is greater than 0. What does this do? Squiggly words. This isn't completed, but oh, this is not the right one. That's what my utility costs. There we go. So first, this should take care of the length, and I also need to care about the first character of S. So I can say E as first character. I can use like access notation as if it's in a column. It's kind of weird with things like this. And I say equals the $sign character. That takes care of the second property. And last one is that if it's parsable into a float, if like the substring after the first is parsable into a float, which is parsable, that's the public function I made before, with the substring after the first character. And so I guess to sort of show what this is doing, I'll just print this out in its current state, which should be a list, not an actual cost, but just to show you what it's exactly doing right now. I'll just run this as is. So we're filtering out the bad strings, right? So this should only be hopefully $sign, properly formatted $sign stuff, which is actually what it ends up doing. So we took out all of that weird, clearly improperly formatted strings, and we're only left with now a list of the actually correct strings with the $sign and amount. But once again, these are still strings, and if I roll over this, we can see it's a list of strings, so I can't really add this up now, right? I want it to be a list of floats. So how can I turn this list of strings into a list of floats? Well, I can map every single string to its proper float map, and hence we will use the map function. So I can assume that these strings are now properly formatted. So now how do I turn a string containing a $sign and amount to the proper float value? Well, I'll basically just parse it to a float after the first substring. So I can say e.substring, and the way to do it in Kotlin is .toFloat. So this usually throws an error if it's not correctly parsable, but the filtering that we did before makes it so anything that then goes into this mapping will always be properly formatted. So we don't have to worry about that. So this mapping will now take the proper $sign strings and turn it into the floats. So you can see what the print ends up doing by running it really quickly. So we had the $sign amounts before, and now with our mapping, we have the actual float values that they correspond to. Awesome. And now the last thing we have to do is actually sum those up. And I could say iterate through every single one with a for loop, but the much more elegant way to do it is with a float function. And my initial value, if I had nothing, would probably be 0, right? 0 just because it's a float. If that's like my default value for my sum. And I've taken an accumulation and an element. And I'll, for every element, take my previous sum so far, which is my accumulation, my sum so far, and add my new element onto the end of that. So finally, this should now say it's actually a float, and I took a note here that the actual total cost of all of those things added up is $731.81. So now we will see if that is what this actually ends up printing as our final sum result. Suspense, and in fact, that is what we end up printing. So we did a pretty complicated task of turning sort of, I wouldn't really call it natural language, that sounds a little bit throwing like keywords in there for the algorithm or something. But we've but we've taken in these sort of human inputs of strings and actually turned them into the proper float amounts and then ended up summing them up. And we did it, and hardly any lines here. This is like 5 lines of code, only 4 lines of actual logic. And if you were to do this with a for loop instead, this would take many more lines of code and probably many lists that you create once and then sort of throw away and never use again. So this is a much more elegant way of doing everything, and I hope this shows the power and elegance of using higher order functions to condense your code. We use these higher order functions again, like all over our code bases on AppDev. They condense code so well, and well, once you understand how to use them, they do seem a little strange at first, but once you understand how to use them, you'll end up coding a lot more concisely and much more neatly. I know when I first saw these on my code bases, or like the code base I'm working on here, when I first got into AppDev, I was like, what is a filter? I just kind of rolled with it, like oh, I don't want to feel like I don't know what I'm talking about, so I'm just gonna pretend I know what this looks like. But once you understand that these are just operating on like arbitrary elements, just one element at a time, it honestly is not hard at all to write your own higher order function applications and use them even on crazy problems like this. But yeah, that's pretty much all I have for the demo playground for today. I hope it got you at least slightly interested in higher order functions and functional programming. I know you've probably seen all this stuff with the Lord himself, Clarkson. But hopefully it gave you also a good sneak peek into what to expect with 3110 if you'll be taking it in the future. But yeah, that is pretty much all for today. Thank you two so much for coming. I was very afraid I would have to do this to a blank audience, but thankfully you two are here. So just a last final announcement. The bonus homework, if you choose to do it, is of course optional. It is just a Jetpack Compose assignment if you'd like to dabble in that and get some extra bonus points. It is due 12/4, I can't read dates, December 4th at 11:59 p.m. Find my mouse now, it's in a couple of weeks, not next week, about 2 weeks from now. So that is pretty much all I have for you today, so thank you two for coming very much.